This is class 11 of my arithmetic course. Today we're going to be talking about fractions and fraction equivalency. We haven't gone over fractions yet, so this is your first lesson in fractions. We're going to be using rectangles to describe fractions. You can use circles, you can use triangles, you can use really any shape to describe fractions, but rectangles are the easiest shapes to use. If you use circles, you can think about pizza or pie or cookies. If you want to use rectangles, I'm going to use a candy bar as an example here. So let's consider these to be candy bars. The entire shape is one whole candy bar. But as you can see, the green part is just a fraction of a candy bar. So a fraction is less than a whole. It's less than one whole. So in this case, we're dividing the fraction up into 5 equal parts. Now it's extremely important to understand that these parts must be equal size, or else the fraction is not going to really make sense. So all these pieces are the same size. So we're dividing this candy bar up into 5 parts, and this is definitely a real-world problem here, because if you've ever had a candy bar, it's bad for your teeth. But this is a real-world problem here. If you want to share this candy bar with your friends or with your mom or your dad, you might divide the candy bar up into fractions of the whole candy bar. So in this case, we have 5. We divide the candy bar, and if you buy candy bars, sometimes the candy maker actually designs the candy bar so you can break it up very easily into parts. And we're going to assume this candy bar is broken up into 5 parts, and we only have 2 out of those 5 parts. So the green part is the only part that's left over. So the fraction of the whole is 2 out of 5, or we say it as 2/5. So the number at the top of the fraction is called the numerator, and the number at the bottom of the fraction is called the denominator. So the reason that the number at the bottom is called the denominator is because the word denominator means it's whatever you're counting. So in this case, we're counting fifths. 1, 2, 3, 4, 5. So the denominator tells us what exactly we're counting. You may have heard the word denomination referring to money. Dollars we use in the United States. If you're in Europe, you might use money called euros. And there are all types of different currencies, but sometimes those currencies are called denominations. It just means the type of thing that you're counting. Another use of the word denomination is to describe a type of a church, a version of a church. You might say there's many different denominations of Protestant churches. That just means there are different versions of Protestantism. So that's what the word denominator means. It tells you what exactly you're counting. But the word numerator, that you can think of that word as just meaning number. That's actually how many of the thing that you're counting. We're counting fifths. That's our denomination. And how many fifths? What number of fifths? 2/5. You don't really have to know all that stuff about where the words come from, but you do have to know that the numbers on the top is numerator and the bottom is denominator, so on and so forth. So the 2 is the green part that's colored in here, and the 5 is the total number of pieces. So that's your introduction to fractions. Now we're going to talk about what I call the fundamental principle of fractions. I'm going to show you what I call the fundamental principle of fractions, just to explain to you what's called fraction equivalency. What that means is we can find different forms of the same fraction. So if I go down here to this next rectangle, and I draw a line straight through it. So let's say that I'm going to divide the candy bar. I would say, well, I don't have 5 friends to divide this candy bar up. I have 10 friends, so I want to divide the candy bar up. I have to draw a line across there like I did. Boom. And now I can divide the candy bar up into 10 parts. But notice that the green part is still the same size. I didn't really increase the fraction. I didn't decrease the fraction. The green part is still there. But now, instead of 2 out of 5, I have 4 out of 10. But the important thing to understand is that 2 out of 5 and 4 out of 10 is the same value. It's the same thing. All right? The numbers are different. The fraction looks different, but it's the same value. That's fraction equivalency. So you're going to use the concept of fraction equivalency thousands and thousands and millions of times in this course, and, well, maybe not millions of times, but as you go into the next course, and throughout your elementary school, middle school. I'm not necessarily advising you to go to school. I'm just saying kids are required to learn this content in the curriculum. You're going to be doing this millions and millions of times throughout your education in the academic world. Fraction equivalency is extremely important. 2/5 is equal to 4/10. Now, let's go on to the other rectangle down here. And what if I draw 2 lines? Now again, you still have the same amount of chocolate. Let's say that the green part is actually chocolate. That doesn't make much sense for chocolate to be green, but I guess it could be green if it had food coloring. You still have the same amount of chocolate. But now you have, if you count these, you have 6 out of a total of 15. So again, 2/5 is the same thing as 4/10, and it's also the same thing as 6/15. So these are all equivalent fractions. It's the same value, but the fraction just takes a different form. So now let's go into one more example. I think you get the point by now, but let's just go into one more example so you can see the trend that's coming up here. So now I'm going to divide the candy bar into. I'm going to draw 3 lines. And these divisions should be equal in size, but you can see that my hand is not very steady, so I'm not. The divisions are not exactly equal. Just keep in mind they're supposed to be equal. All right. I'm not going to get a ruler here. I don't have time for that. But now we have 8 out of 20 parts. And again, the most important thing to understand is you still have, if the green part is the chocolate that's left over, you still have the same amount of chocolate. All right? It's not changing. So you have 2/5 is the same thing as 4/10, and it's the same thing as 6/15. It's the same thing as 8/20. The only difference is that the pieces are smaller. All right? So now we're going to demonstrate the fundamental principle of fractions. What we did when we drew this line is we multiplied 2 and 5. We multiplied both those numbers, 2 and 5, by 2. Let me get rid of that highlighter. So we took 2/5 and we multiplied both sides by 2 to get 4/10. So what you're going to find is, well, let's just go on to the next one. So then in the second one, we had 2/5 and we multiplied 2/5 by 3. We multiplied both sides, the numerator and the denominator, by 3 to get 6/15. And in the next one, we multiplied 2/5 by both sides by 4. It's the most important thing to understand is we're multiplying both the numerator and the denominator by the same number. And we got 8/20. So the fundamental principle of fractions is this. Now get ready for this. Pay attention. Concentrate. This is one of the most important things you're going to learn in this entire class. You cannot forget this. Don't ever, 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 ever forget this. in this class, the next class, the next class, the next class. Don't ever violate this rule. When you want to find a different form of a fraction, you can multiply both sides of the fraction by the same number, and that fraction will not change. Okay, but you can't multiply the bottom, for example, you can't multiply the bottom by 2 and then the top by a different number, right? If you're going to change the form of a fraction, if you're going to change it from 2/5 to 4/10, you have to multiply both sides by the same number, all right? Now, I know that doesn't sound very interesting now, but trust me, this is the most important principle of fractions. Down here, on this problem, we multiply both sides by 2. And this problem, we multiply both sides by 3. And in this problem, we multiply both sides by 4. We always multiply the numerator and the denominator by the same number. So that's what I call the fundamental principle of fractions. We're going to use this a lot throughout the class. Now, we have another example. So now we're going on to a different fraction. I'm not going to bore you by showing you by going on and on with this, but now you have 1/2. Before we had 2/5, now we're doing a different fraction. So 1/2, you can change to 2/4 by multiplying both sides of the fraction by 2. Down here, we multiplied both sides of 1/2 by 3 and got 3/6. Down here, we multiplied both sides by 4 and got 4/8. So all these fractions, 2 out of 4, 3 out of 6, 4 out of 8, those are all the same fraction. They're all the same thing as 1/2. So we're just finding different forms. And I know what you're thinking. You're thinking, well, who cares? I don't care about this. Well, you're going to care as we go into the next class and the next class and the next class, and throughout your entire academic education, you're going to care about this. Trust me, because you're going to be required to use fractions millions and millions and millions of times. Now, I just want to discuss an important principle here. If you can multiply both sides of the fraction and get an equivalent fraction, then that stands to reason that you can divide both sides, because division is just the opposite. In other words, if you want to go from 1/2 to 4/8, can't you go backwards? Can't you go from 4/8 back to 1/2? Well, if you want to go backwards, you have to do the opposite of multiplication, which is division. So the fundamental principle of fractions is not just that you can multiply both sides of a fraction by the same number, and keep in mind it's got to be the same number, but you can also divide both sides of a fraction by the same number. So that's the fundamental principle of fractions. For example, if you have 40 over 60, if you divide both sides by 2, then you get 20 out of 30. 40 out of 60 is the same as 20 out of 30. And you can also say 40 60ths or 20 30ths. You can also take 40 out of 60 and divide it by 10 and get 4 out of 6. 40 out of 60 is the same as 20 out of 30, which is the same as 4 out of 6, which is the same if you divide both sides by 20, you get 2 out of 3. All these fractions are what you call equivalent fractions. They give you the same value. In other words, if you had a big old candy bar that you could divide up into 60 parts or 30 parts, it wouldn't make any difference. It's still the same amount of chocolate. So now I just want to say real quickly that if you have some fraction, let me just give you a random fraction, let's say 5/7. You cannot add a number to both sides and get an equivalent fraction. If you get like 7 out of 9, that doesn't work. So do not do that. All right? So I'm going to make a little note there. Don't do that. Don't subtract. Don't do anything except multiply both sides of the fraction by the same number. And the key word is same number. It's got to be the same number. You can't, that's another important point. You can't take a fraction and multiply the top by 2 and then multiply the bottom by 3. Okay, that doesn't, that gives you 10 over 21, but 10 over 21, if you draw a chocolate bar and you carve out 10 out of 21 parts, that's not going to be the same as 5 out of 7 parts. It's not equal. It doesn't work. When you put a slash through an equal sign, it means not equal to. So just keep in mind that's not correct. So it's really important to keep the fundamental principle of fractions straight in your mind, or else this stuff is going to get really confusing as you go on. But as you can see, this is pretty easy stuff. No big deal. As long as you remember the fundamental principle of fractions, this class is going to be pretty easy. unless you didn't memorize your multiplication facts. I'm not going to keep going on and on about memorizing your multiplication facts, but if you didn't memorize those facts, man, you're not going to make it through this class. I'll tell you that right now. Alrighty. So that's your introduction to the fundamental principle of fractions. So now we're going to go ahead and do some practice problems. Number 1, find 3 fractions that are equivalent to 3/4 by using multiplication. So let's do this one together, and then you can do the next one on your own. So let's multiply 3 and 4 by 2. 3 times 2 is 6. 3 times 2 is 6. 4 times 2 is 8. 8/6 is the same thing as 3/4 if you carve out the candy bar. All right, now let's put a comma there. Let's multiply 3/4, both sides of 3/4 by 3. 3 times 3 is 9. 3 times 4 is 12. That's another fraction. Let's multiply both sides of 3/4 by 4. 3 times 4 is 12. 4 times 4 is 16. So we found 3 fractions that are equivalent to 3/4 by using the fundamental principle of fractions. Now, just to mention real quick, I don't know if anybody else calls it the fundamental principle, but I just like calling it that because it's so important for this class and for your entire academic education that you understand this principle. All right, so again, you can multiply both sides of the fraction by the same number. So this stuff is really easy. Now you try number 2, stop the video, and when you come back, we'll do it together. All right, we're back. Find 3 fractions that are equivalent to 8/9 by using multiplication. Let's multiply 8/9, both sides of 8/9 by 2, and you get 16 over 18. Multiply both sides by 3, you get 24 over 27. Multiply both sides by 4, you get 32 over 36. So again, we're just using the fundamental principle of fractions. And if you're struggling with your multiplication facts, then that's not my problem. That's your problem. You should have memorized the multiplication facts. All right. Try number 3, and when you come back, we'll do it together. All right, we're back. Find 3 fractions that are equivalent to 4/11 by using multiplication. Multiply both sides by 2, you get 8 over 22. Multiply both sides by 3, you get 12 over 33. Multiply both sides by 4, you get 16 over 44. And there you go. Now, I should mention also that there are other forms. You can keep going forever. You can multiply both sides by 100. You get 400 over 104. What would that be? 100 times 11, that would be 1100. So 400 over 1100. You can multiply by all kinds of different numbers. So if you got different answers, you may not have done it necessarily wrong. But anyway, let's go on to the next problem. Now, remember I said you can multiply both sides of the fraction by the same number, right? Well, you can go backwards and you can divide. So that's what we're going to be doing in number 4. Find 3 fractions that are equivalent to 100 over 300 by using division. So I can see immediately that we can divide both sides by 100 because 100 goes into 100, right? So 100 divided by 100 is 1, and 300 divided by 100 is 3. I can also divide both sides by 2. 100 divided by 2 is 50. It's like if you have $100 is 100 cents, you divide it $1.50, you get 50 cents. 300 divided by 2 is 150. That's another equivalent fraction. Again, we're just using division now. We're just going backwards from multiplication. Now, what else can we do here? We can divide both sides by 10. 100 divided by 10 is 10. 300 divided by 10 is 30. So those are 3 equivalent fractions. So now you try number 5. When you come back, we'll do it together. All right, we're back. Let's try dividing both sides by 100, and you get 2 over 7. Divide both sides by 10, and you get 20 over 70. Divide both sides by 50, and you get 4 over 14. So you may have different fractions. Let's just do some other ones just so you can, if we take this fraction, I'm kind of cheating here. I'm taking this fraction, but you can start with any of these fractions. If you divide this fraction by 5, you get, well, actually, I guess you'd still get 20 over 70, or 4 over 14. But the point is, you can find more of those fractions. We don't really have time to keep finding more and more fractions, but if you found some of these fractions, then you did those correctly. I can't speak for the other ones that you got, or maybe you got the same 3. Now try number 6. Again, we're using the fundamental principle of fractions here. You can multiply both sides of a fraction by the same number, or you can divide both sides of the fraction by the same number. Try number 6, and when you come back, we'll do it together. All right, we're back. Let's try dividing both sides by 2. Then you get 8 over 12. Try dividing both sides by 8, and you get 2 over 3. Try dividing both sides by 4, and you get 4 over 6. These are all equivalent fractions that we got with the fundamental principle of fractions by simply dividing both sides by the same number. You have to divide or multiply by the same number, or else it doesn't work. All right, number 7. Try number 7, and when you're done, we'll come back and do it together. All right, we're back. Divide both sides by 2, and you get 6 over 24. Divide both sides by 3 works, but it's kind of hard if you don't. It's kind of hard to do that one. So let's divide both sides by 6, and you get 2 over 8. Divide both sides. We can actually divide both sides by 12. You don't know 12 times 4, but 12 times 4 actually ends up being 48. So if you divide both sides by 12, you get 1 over 4. And what else can we do? If we divide both sides by 3, then we don't really need to go any further, but I just want you to, if you had different ones, I want you to see what happens there. I think that would be 4 over 16. And you can just keep going. I'm not going to bore you by keep finding more of those, but hopefully you found some of those equivalent fractions. All right, so that's those are some practice problems. So we've learned we've learned what fractions are. We learned that the top number is called the numerator, the bottom number is called the denominator. We learned how to find equivalent fractions using the fundamental principle of fractions. And what is the fundamental principle of fractions again? Can you tell me? You can multiply both the numerator and the denominator by the same number, or you can divide the numerator and the denominator by the same number, and the fraction does not change. The numbers change, but the value of the overall fraction does not change. Now, at this point, we're going to go on to another problem. We have 32 over 40. Whoops. We have 32 over 40. And what we're going to do is we're going to divide both sides. We're going to reduce the fraction. What we were doing in the previous example, when you divide, when you make the numbers smaller, see in every case here, we had 12 over 48, and we made those numbers smaller. When you divide and make the numbers smaller so that you get the lowest numbers possible without going into fractions. If you have fractions in the numerator and fractions in the denominator, that's something called a complex fraction. We're not going to go into that until you're not going to learn that until my beginning algebra class, or Algebra 1 is another name for it. You're going to take this course, and then after this course is pre-algebra, and then after that it's beginning algebra. Then you're going to learn about complex fractions. But in this course, you don't have to worry about that. But when you divide both the numerator and the denominator and make the numbers as small as possible, notice we got 6 over 24, we got 2 over 8, we got 4 over 16, but the smallest numbers possible were 1 over 4. When you reduce a fraction, when you change the form of the fraction, when you find an equivalent fraction by dividing and making the numbers smaller, and you get to the smallest numbers possible, that's called reducing the fraction. We want the smallest numbers possible. So I'm going to give you a bunch of fractions down here. And I'm going to ask you to find the smallest numbers possible by using the fundamental principle of fractions. We're going to divide both sides by the same number until we get the smallest possible numbers. And again, the reason we want to do that is because why would I say I want 5/10 of that pizza when I can just say I want 1/2 of that pizza? You know, why would I say if I want 1/2 of your dollar, why would I say give me 50 out of 100ths of your dollar? I mean, actually that might make sense because there's cents, but why would I say give me 500 out of 1,000 of your dollar? Why would I say that when I can just say give me 1/2? 1/2 is much easier than 500 over 1,000 or 50 over 100 or 25 over 50. So we want the smallest numbers possible. So I know my multiplication tables, or my multiplication facts, so I know that if I divide 32 by 8 and 40 by 8, then I can get, I should write these, so that's 32 by 8 and 40 by 8, then I get 4 over 5. So 4 over 5 cannot be divided any further, so we say that 4 over 5 cannot be reduced any further. So I don't want 32 over 40. Those numbers are too big. I want 4 over 5. Again, you're not going to say to your friend, give me 32 over 40 of your candy bar. You're going to say, give me 4/5 of your candy bar, because that's much easier to say. It's much easier to think about the smaller numbers. Now, even though these are smaller numbers, the pieces of the candy bar are going to be bigger. So just keep that in mind. When you're dealing with fractions, everything kind of is reversed. All right, so, and also when you reduce a fraction, you know, you can reduce it by steps, but when you go to the smallest number, that's called reducing to lowest terms. All right, but again, you have to know your multiplication tables in order to do this. So for number 9, let's do another one. What I'm asking is, I want to divide both numbers, but the big question is, what number divides into both 72 and 81? And that's going to help me reduce. So I know my multiplication tables. I recognize 72 and 81. I recognize those numbers as products of 9. So I know if I divide both sides by 9, 72 divided by 9 is 8, and 81 divided by 9 is 9. So you see, I reduced the numbers significantly by knowing my multiplication facts. 8 over 9 is much easier to understand than 72 over 81. Now I just want to demonstrate a principle here. I could have divided both the numerator and the denominator by 3, and that still would have worked. If I divide 72 by 3, then I get 24. And if I divide 81 by 3, I get 27. So I still reduced the fraction, but I didn't go to lowest terms. Now you can do it that way. You can do it by steps. You can divide both sides by 3 to get that. Then you can take this fraction, and you can divide both sides by 3 again to get this fraction. So you can do it by steps if you really want to. But it's easier to just go straight to the answer, straight to 8/9. But the only way that you can do that, the only way you can have the power to do that is with your multiplication facts. So again, if you don't know your multiplication facts, you're going to be struggling here. So now that's pretty much everything that you need to know. Don't get up and walk away. Sometimes when I say that's the only thing you need to know, kids get up and walk away. Don't go anywhere. We're not done yet. Don't get your hopes up. So that's everything you need to know in order to do the rest of the problems. All right. So now you try number 10. Again, we're reducing the fractions, which means we're dividing. And when we go on to the next class, we're going to use multiplication to find bigger numbers. There are some cases when you're adding and subtracting fractions, you have to find a bigger number, so you're going to be multiplying. So we're going to use the fundamental principle of fractions today to reduce fractions. You're going to use the fundamental principle of fractions in the next class to find fractions with bigger numbers so that you can add or subtract them. And you're going to keep using this principle over and over again. But today we're mostly going to be using the division principle. You're going to divide both sides of the fraction by the same number. So divide both sides of 8/10 by some number that goes into both 8 and 10, and see if you can get the smallest numbers possible. When you come back, we'll do it together. All right, we're back. So 8/10, I know that 2 times 4 is 8, and 2 times 5 is 10. So I know I can divide both sides by 2 to get 4/5. So if you did that correctly, pat yourself on the back. If you didn't, that's completely fine. We're going to go on to the next problem. And you can try the next problem. 56/64. Now you should recognize those numbers because those numbers are products that we learned when we went over multiplication facts. If you don't know your multiplication facts, you're not going to be able to go very far today in this class. So if you don't know the multiplication facts, go back and learn them. Try number 11. When you come back, we'll do it together. All right, we're back. I know that 8 times 7 is 56, and I know 8 times 8 is 64. So I know I can divide both sides by 8. 56 divided by 8 is 7. 64 divided by 8 is 8. And that's the quickest way to get there. Now you could divide both sides by 4, or you could divide both sides by 2, but that would take a lot longer. The fastest way is to find what's called the greatest common factor. And we're going to go over factors. We haven't talked about factors yet, but we're going to go over that later on. It turns out that this number is called the greatest common factor because it gets us to these numbers in the quickest way possible. And you don't really need to know that term greatest common factor or factors in order to do these problems, but you are going to need to know those terms in order to go into upper math courses and whatnot. Sometimes you need to know things in school that are not really necessary. In fact, that's most of what school is learning a bunch of stuff that you may not need to know in the real world. Number 12, 35/49. Go ahead and do that one on your own. And when you come back, we'll do it together. Again, you have to divide both sides by the same number. All right? 35/49. All right, we're back. I know 7 times 5 is 35, and I know 7 times 7 is 49. So I can divide both sides by 7, and I get 5/7. So if you got that one correct, pat yourself on the back. If you didn't, that's okay. We're going to do another one. 7/18. Now this one is kind of a trick problem. You know why? Because this one can't be reduced. We can't go the numbers. We can't reduce the numbers. We can't make them smaller anymore. So for this one, you say cannot be reduced. You can just put CBR. All right? But number 14, that one can be reduced. So use your multiplication facts and your concept of division. Remember, division is the opposite of multiplication. So if you know your multiplication facts, you can go backwards and find one of the numbers that we're multiplying to get 15 or 24, and that's the whole principle here. Try number 14, and when you come back, we'll do it together. All right. I know 5 times 3 is 15. And I know 5 times 5 is 25. So I can divide both sides by 5. 5 goes into both those numbers. When I say 5 goes into both those numbers, I just mean 5 times something equals those numbers. So 15 divided by 3 is 3, or 15 divided by 5, is 3. 25 divided by 5 is 5. All right, so if you got that problem right, great. If you didn't, no problem. Just figure out what you did wrong. Again, the most important principle to understand here, never, never, never forget, we're dividing both sides of these fractions by the same number. You have to divide by the same number or else it doesn't work. The candy bar is not going to be the same fraction. It's not going to be the same amount of chocolate if you don't do it correctly. All right. So in this problem, our multiplication facts are not going to be quite powerful enough to get us to the answer immediately. It turns out that with this problem, the greatest common factor, which we want to divide both sides by, is going to be actually 24. We're not aware that 24 times 2 is 48. We're not aware that 24 times 3 is 72. So in this case, we're actually going to have to reduce in steps. We do know that 6 times 8 is 48, and we know that 6 times 12 is 72. Actually, we didn't know that either, now that I think about it. 6 times 12, we don't know that one. Actually, we do know, how about 8? 8 times 6 is 48, and 8 times 9 is 72. So see how I'm playing around with these numbers? I don't know what it's going to be. I'm just playing around with my multiplication facts. So we're going to divide both sides by 8. I tried dividing both sides by 6, but 6 times 12, we may not be aware of that one, so we'll try dividing both sides by 8. And we get 6 over 9. Now the reason that this is, again, a different problem is because 6 over 9, that can still be reduced. So we're reducing in steps. Now if we divide both sides of 6 over 9, by 3, divide both sides by 3, then we get 2 over 3. So it's pretty much, it's the same thing we were doing before. The only difference is we had to do 2 steps on that one. And it's okay to do multiple steps. It just takes a little longer. 50 over 60. See if you can, what should we do with that one? Which number goes into 50 and 60? See if you can do that one on your own, and when you come back, we'll do it together. All right, we're back, number 16. We actually know these multiplication facts. We know 10 times 5 is 50, and 10 times 6 is 60, so we can divide both sides by 10. That one wasn't such a big deal. We actually didn't need to do multiple steps on that one. 17. What can we divide into 9 and 30? That one that our multiplication facts encompasses that problem. So do that one, and when you come back, we'll do it together. All right, we're back. I know that 3 times 3 times 3 is 9, so I can divide the top by 3. And I know that 3 times 10 is 30, so I can divide the bottom by 3. Again, we have to divide the top and bottom by the same number, and then we get 3 over 10. And that's completely reduced. Also, I should remind you, this is also called reducing to lowest terms. All these fractions are now in lowest terms. We can't reduce them any further. All right, try number 18, and when you come back, we'll do it together. All right, we're back. Divide both sides. The quickest way to do it is to use your multiplication facts and divide both sides by 4, and you get 3 over 5. And that's reduced to lowest terms. Now, number 19 is a little different. because a lot of students, when they're trying to figure out what number you can divide both the numerator and the denominator by, a lot of times they forget that you can actually divide a number by itself. We can divide 5 by 5. A lot of students would look at this problem and think, well, I don't get it. I can't find anything. But remember, you can divide 5 by itself. And does 5 go into 45? If you know your multiplication facts, you know it does. 5 times 9 is 45. So we can divide both the numerator and the denominator by 5. I don't know why that window keeps coming up. I'm sorry about that. I'll figure that out eventually. Maybe Microsoft will help me with that, or somebody. All right, 5 divided by 5 is 1. 45 divided by 5 is 9. And we have 1/9. So again, remember, you can divide a numerator by itself or a denominator by itself. All right, so why don't you try number 20, and when you're done, we'll come back and do it together. All right, we're back. Which number can we divide into 100 and 500? It has to be the same number that divides into both 100 and 500. Well, you could divide both sides by 50 and you get 2 over 10, but that's not reduced completely. You can divide both sides by 2 and you get 50 over 250. You can divide both sides by 25 and you would get 4 over 20, I believe. But the fastest way to do it is just to divide both sides by, again, what we call the greatest common factor, which is 100. And you get 1 over 5. That's the fastest way to do it. If you didn't do it the fastest way, that's okay. You can do it by steps. The most important thing to understand is that when you're reducing the fraction, you have to divide both sides by the same number, or else it doesn't work. It's not going to give you the same fraction. All right, why don't you try number 21, and when you come back, we'll do it together. All right, we're back. 44 and 77, those numbers look really familiar. Remember, when the two numbers are the same, they're right next to each other, that means we can divide by 11. 44 divided by 11 is 4, 77 divided by 11 is 7. And there we go. All right, number 22. Try number 22, and when you come back, we'll do it together. Remember, you have to know your multiplication facts. So go ahead. All right, we're back. Divide both sides by, divide both sides by, actually 9 would be the best one. And you get 2 over 3. Try number 23, and when you come back, we'll do it together. All right, we're back. Knowing my multiplication facts, I know that I can multiply, let's see here. Actually, I'm not sure about this one. Actually, 6. I think 6 goes into both of those. So divide both sides by 6, and we get 4 over 9. But that fraction's not reduced. It's not, or actually, no, it is reduced completely. What am I talking about? There you go. All right, we can't go down any further. Try 24 is a trick problem. Why don't you try 24? And when you come back, we'll do it together. All right, we're back. I said 24 is a trick problem because it cannot be reduced. Whenever a fraction cannot be reduced in these problems, just write CBR. All right, try 25, and when you're done, we'll come back and do it together. All right, we're back. Divide both sides of the fraction by 2. And we get 5 over 12. and that's reduced to lowest terms. Try number 26, and when you come back, we'll do it together. All right, we're back. Let's divide both sides by, let's see, what number multiplies to equal 28 and 42. I'm thinking about my multiplication facts here. 7. I think it's going to be 7. 28 divided by 7 is 4 because I know 4 times 7 is 28. And 42 divided by 7 is 6 because I know 6 times 7 is 42. That number is not reduced completely though. Let's see, was there a bigger number we could have used there? Let's see. Trying to think if there was a faster way to do that. I don't think there was. So this is a problem where we actually have to use 2 steps. So now we have to divide both sides by 2. To get the final answer, which is 2/3. So if you got 2/3, that was a good one. Good job. If you didn't, that's completely fine. We're going to keep doing more of these. Yep. 27. Try number 27, and when you come back, we'll do it together. All right, we're back. 20 over 30. We can divide both sides by 10. That's the fastest way to do it. There are other ways to do it, but that's the fastest way, and you get 2/3. Turned out we got the same answer as we got in 26. All right, go ahead and try 28. All right, if you divided both sides of this fraction by 9, you're probably on the fastest track. 81 divided by 9 is 9. 90 divided by 9 is 10. And it's now reduced to lowest terms. All right, so you should be getting a feel for how this works. Again, this is called reducing fractions, and when you go to the smallest numbers possible, it's called reducing the fractions to lowest terms. All right, now for number 29, let's see here. I think for number 29, we're going to go into some fractions where, like I said, we have to reduce with multiple steps. But I'm going to show you a slightly different way to do this. It's called factoring. This number, I mentioned before, this number is called the greatest common factor because when we divided both sides, we went straight to the smallest numbers. That we went to lowest terms immediately. So we're gonna talk about factoring and finding the greatest common factor because that's going to help you figure out how to reduce the fractions quickly. Now, like I said, you don't have to know the method. I mean, if you understand everything that we've done so far, you're pretty much I'm going to say you're pretty much done with the actual concept, but I hate to say done because whenever I say done, kids get up and walk away. Don't walk away. But what I mean is you understand how to do these problems, and you've got what you need. You're going to need more practice that we're going to do here, so don't leave. But what I mean is you have what you need to do all these problems. But you're going to need to learn something called factors and greatest common factor because that's often used to describe how to reduce these fractions in the best way possible. But again, you don't need to know these terms to actually do the math, but you are going to need to know the concept of factors and the concept of the greatest common factor when you go into upper math courses because they're going to ask you what is the greatest common factor of two numbers, and you're going to have to figure it out, whether or not you're doing a reduction problem or not, whether or not you're reducing a fraction or not. So this is some stuff that is not hugely important for this class at this point, but I'm just going to show you because like I said, it's necessary to know this. So we're going to reduce this fraction just like we did before. But the difference is we're going to use something called factoring. So we're going to factor. I know 4 times 7 is 28. Now notice I wrote a dot there. There's actually different, we haven't learned dot notation. There's different notations for multiplication, and why is there a different notation used? Well, a different notation doesn't have to be used, but just because of the history of math and the tradition, there are different notations for multiplication. You learned crosses for multiplication, so we could have written 4 times 7 with a cross. You're also going to learn this dot notation. When you go into upper math courses, you're going to learn parenthesis notation. And so I know what you're thinking. You're thinking, why do we have to use so many different types of notation? Well, again, we don't have to use it, but that's just what mathematicians do. So you have to learn all the notations. And the reason that dots are used at this point is because crosses just get it starts to get tiring to have to write crosses over and over again. So dots just make it easier. So that's why we're moving on to dots for multiplication. Now I know the bottom is 8 times 8. All right. So you're probably thinking, well, how has this helped us so far? Well, it hasn't helped us so far. But if we keep on factoring, 4 becomes, I know 4 is 2 times 2. And I know 8 is 4 times 2. So I changed this 8 to 4 times 2. And so now, when I was looking at these numbers, I couldn't really find a multiplication fact that was helping me. So I used the factoring method, and now I can see that there's something that will go into both 28 and 64. Let's see here. If I recombine the 2 times 2 here and just keep that as a 4, I see I have a 4 on the top and a 4 on the bottom. So what we're going to do is we're going to do what's called canceling out. If we divide, if you multiply 4 times 7, you get 28, right? But if you divide 28 by 4, you get back to 7. It's just the opposite. So we know that if we divide this number by 4, we'll just end up with a 7. And we know if we divide this number by 4, we'll just end up with whatever 8 times 2 is. So all that's just a lot of complicated stuff just to mean that if you have a number on the top and on a number on the bottom, you can do what mathematicians call canceling out. So again, I know that sounds really complicated, but that's all you really need to know, that you factor the numbers. Factoring means you break the numbers apart into a product, a multiplication expression, and then if a number is on the top and the bottom, you can just make it disappear. And so if it disappears, the 4 disappears, you end up with 7 over 2 times 8. And you can recombine the 2 and the 8 because 2 times 8 is 16, so you end up with 7 over 16. So this is just a different way to reduce the fractions. You don't have to do it this way, but when you get to numbers that are big enough to where our multiplication facts are not working, this method is really useful. All right, 4 over 48. Let's try another one of those. I'm going to factor the top to, let's see here. I'm going to factor the top. I'm just going to keep the top. But I'm going to factor the bottom to 6 times 8. We know 6 times 8 is 48. All right, now this is starting to get confusing, so I want to put a line here. It's perfectly fine to write lines to organize your work. There's nothing wrong with that. So now I'm going to change 8 to 2 times 4. So I have 6 times, not 8 anymore, not 6 times 8. I'm going to change it to 2 times 4 because I know 2 times 4 is 8. Again, this 8 turned into 2 times 4. And now, it's just a coincidence. The last problem we had 4 as a common factor, but now we have 4 again as a common factor. So the 4's just cancel out. That was a coincidence that they just end up being 4's again. So now, in the bottom, if the 4 cancels out, I'm just going to end up with 6 times 2, which is 12. And in the top, the 4, if the 4 disappears, it just becomes a 1. Because you're probably thinking, well, wait a second, if the 4 disappears, then doesn't it just become a 0? Well, no, technically what we're doing, we're still using the fundamental principle of fractions. We're dividing both sides. When you cancel 4 out, what we're really doing is we're dividing both sides by 4. Again, with the previous problem, if 4 times 7 is 28, then you know if you divide 28 by 4, you just get 7. So when we get rid of the 4 on both sides, we're dividing both sides of the fraction by 4. So when you divide in the number 30, if you divide the 4 by 4, it's not 0, it's 1. All right? So that's something that students can get confused with. So 4 over 48 reduces to 1 over 12. Let's see here. So 50 over 75, again, that's a problem where my multiplication facts aren't going to help me. So I'm going to use the method of factoring. So I know 50 is 5 times 10, and I know 75 is 3 times 25. And I also know that for the bottom, I know that 25 is 5 times 5. So again, I couldn't use my multiplication facts directly to reduce, but now I'm using my multiplication facts to kind of do it, I guess you could say we're doing it by steps again, but we're doing it by the method of factoring. So now I'm going to factor the 10 even more. I mean, I could go ahead and just cross out the 5, but then I end up with 10 over 3 times 5, and you might think, well, we're done at that point. Well, you can actually keep going. The top I can continue to factor. Let me move this problem down. I can continue to factor the top. The 10 is 2 times 5, and the bottom is 3 times 5, so we can cross out more 5s, and we ultimately end up with, and I'm going to violate the cardinal rule, I'm going to go to the left, but sometimes that's just necessary. Final answer is 2/3. You should never go up to the left like that. You should always go down and to the right, but as you can see, I don't have any room left over, so forgive me on that. All right, so what is that? Let's see here. What are we doing now? Number 32. Factoring. We talked about factoring, right? So at this point, we're going to discuss more about factoring to help you reduce fractions. Now, again, I want to point out that I'm talking about factoring mostly because you're going to need to know this for upper math courses and, middle school entrance exams, high school entrance exams, whatever tests the people are going to give you. You're going to need to know the concept of factoring more for that than for reducing fractions. You already know how to reduce fractions after doing all those problems. What I'm about to show you is mostly just it's mostly just so that you will recognize what these terms mean when you see them on tests and upper math courses. We don't really need this to reduce fractions, but it is something that will help you. So it's related. And what we're going to learn next. Again, we went over factoring, so what we're going to learn next is called factor trees. I didn't use factor trees to factor, for example, 50. I just wrote it as 5 times 10. But one method that is typically used is factor trees. So instead of going from left to right, I'm going to go down, and we're going to factor 90 using a factor tree. And I'm going to move this down. So I'm running out of room here. Excuse me. Just move that down there. So 90, I know that 90 is, we can do it a lot of different ways, but I know that 90 is 9 times 10. So I'm using these lines here, going to the left and right and down. And I know that 9 factors to 3 times 3. I want to put a dividing line here. It's always good to put dividing lines. That's perfectly fine. And I know that 10 is 2 times 5. And I can't go any further. So that is called a factor tree. Now, that's one way to factor 90, but there are other ways. For example, I know, you don't know this from your multiplication facts, but I know that 2 times 45 is 90. And again, you don't have to know 2 times 5. You don't have to know 2 times 45 is 90. Don't worry about that. I just know that from experience. Now, the 2 is done. Notice how I added another line down here. The 2 is done, so when we go on to the next step, I'll just have to bring it down with another line. So, but the 45, we use 2 branches. 45 I know is 9 times 5 for my multiplication facts. And 5 and 2, they're done. We can't go any further, but we do have to bring those down. But 9, we can branch into 3 times 3. Again, these are called factor trees. And so we're done. But here's the important part. Notice that these numbers are exactly the same as these numbers. So these are called factor trees. Now I know again, you're probably thinking, well, why do we need to use this? Well, that's my point. You don't need to use it to reduce fractions, but you do need to know this because people are gonna ask you what a factor tree is, and I just want you to know what it is. All right. If you say I don't know what a factor tree is, then they might try to accuse you of not learning what you need to learn, and I don't want you to be in that situation. So 90 is. I'm just going to do another. The whole purpose of doing these 3 different methods is just to show you that there's more than one way to draw your tree based on how you factor it, but you get the same answer at the end. Let's try 3 times 30. So 30 branches into 3 times 10, and the 3 you can't do any more, so you just bring it down. These 3s you're done again, so you just bring them down, but 10 branches into 2 times 5. And by the way, we should be putting dots in between all these numbers down here. Here also, and here. So at that point, we're done again. So in every case, we have 3 times 3 times 2 times 5. We had 2 times 3 times 3 times 5. It's all the same thing. We have 2 3s, 1 2, and 1 5. All right. Let me just move this up a little bit. All right, now it's traditional to write the final number with the final factorization with the smallest number first, and just order them from least to greatest. So that's our answer: 2 times 3 times 3 times 5. That's the complete factorization. So, but we're gonna to write this final answer, we're gonna use something called power notation. Now you haven't learned power notation, but power notation is really easy. For example, if I have, let's say that I have 7 times 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 7. Okay. But I don't want to write all those 7s. It's much easier for me to use power notation. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's much easier for me to just say 7 to the 11th power. All right, that's power notation. So power means you're multiplying. You're going to be multiplying the numbers. So instead of writing 3 times 3, we're going to write 3 to the 2nd power. Why to the 2nd power? Because there are 2 3s. That's called power notation. So our final answer is going to be that expression. All right. So we learned factor trees. I don't want to spend that much time on this because again, it's not the most important thing. But we learned factor trees. We learned power notation, as you can see down here. And there's one more thing that we have to go over. We factored these numbers all the way down to this point. This point, the bottom point, has a special name for it. It's called the prime factorization of 90. our final answer is the prime factorization of 90. Now, why is it called the prime factorization? Because all these numbers are called prime numbers. These numbers up here are not prime numbers. Prime numbers are simply numbers that cannot be factored any further. That's it. No big deal. So if numbers can be factored, or if numbers are factored, or if a number cannot be factored anymore, it's called prime. And if a number can be factored, if it can be factored, then it's called composite. And I'll show you how to spell that later on, but let's just do some more factor trees here. We'll come back to the whole idea of prime and composite. So the problem is going to be find the prime factorization of 48. You're going to take 48, write it at the top. In fact, let's go ahead and write it up here. All right, so we're going to break it up into branches. I know 48 is 6 times 8. You want to use your multiplication facts. It'll make this go a lot faster. And I know that 6 is 2 times 3. And I know that 8 is 2 times 4. But we can keep going because 2 times 2 is 4. And just bring down the other numbers. And remember to write dots in between the numbers. And so the final answer if you write the numbers from least to greatest, you have 2 times 2 times 2 times 2 times 3. But we don't want to write all those 2's, so we're going to use power notation. We're going to say 2. How many 2's are there? We're multiplying 4 2's, so it's 2 to the 4th power times 3, and rectangle your answer. All right. So let's try another one. I'm going to put a divider here. See if you can do 34 on your own. Find the prime factorization of 50. All right, so let's do it together. 5 times 10 is 50. 2 times 5 is 10. And you're pretty much done at that point. So now we can say, write the smallest number first, then the other numbers. But instead of writing 5 times 5, we can write 2 times 5 to the what power? There's 2 5s, so it would be to the 2nd power. And that's our final answer. So that's using factor trees, and we learned about prime numbers. Prime numbers are numbers that you cannot factor further. Composite numbers are numbers that you can factor further. And we learned the concept of factoring. This is called factoring when you break a number up. Up here, we took 50 and we broke it up into 5 times 10. That's factoring. That's what we've done down here. We took 8 and broke it up into 2 times 4. That's factoring. We learned prime factorization. These are prime numbers because they can't be factored anymore. And we learned that these numbers are called composite numbers. So now for number 35, answer me this question. Is 8 composite or is it prime? You're going to have to know, again, the difference between composite and prime, not because it's absolutely necessary to reduce fractions, but just because you might be asked this question in advanced math courses or courses beyond this math course, or you might be asked problems on a test tomorrow. You never know. This is just part of the curriculum. You're expected to know this. So can you break down 8? Can you factor it further, or can you not factor it further? So see if you can do that one, and when you come back, we'll do it together. All right, we're back. Is 8 composite or prime? Well, I know that if I break 8 into, we can do a factor tree, or we can just write it side to side. I can break it up into 2 times 4, and that can be broken up into 2 times 2 times 2. And I can also do a factor tree, 2 times 4. I don't really have enough room, but you get the point. So obviously 8 can be reduced further, or excuse me, it can be factored further. So that means it is composite. It's a composite number. So the answer is yes, it is excuse me, that's not the right answer. The answer is composite. They want to know if it's composite or prime. It is composite. All right, so tell me if 36, for number 36, is 7 composite or prime? Well, if you said it's prime, you're correct. We can't factor 7 any further. We can't break it down any further. Is 15 composite or prime? Well, if you said it's composite, you're right, because 15 is equal to 5 times 3, so we could break it down further, which means that it's not prime, it's composite. What about 28? Is 28 composite or prime? If you said it's composite, you were correct, because 28 is equal to 4 times 7, which means you can break it down further, so it is composite. All right. So at this point, let's see here. I want you to do the rest of the problems, and you're going to use the method of factoring to solve these. Now you can use a factor tree, but in my opinion, factor trees you need to know factor trees. You need to understand how to use them. But I'm not going to require you to actually use them to solve these problems or to reduce these fractions. So again, we're just going to keep reducing fractions like we were before, but we're going to use these other methods. So you don't have to use a factor tree, but I do want you to use at least try the method of factoring going from side to side. So this is what I mean. So I guess I'll do number 39. You can do the rest. So 75 is 3 times 25. And 120 I know is 12 times 10. And let's keep going. I don't see any common factors yet. These are not common, so let's keep factoring. 25 is 5 times 5. And I know 10 is 2 times 5, so now we have a common factor. So we can cancel out these 5s, and we end up with yeah, I think that's all we can do. So we can just recombine. We end up with 3 times 5 over 12 times 2, which is equal to 15 over 24. Actually, no, I just realized that we still have a common factor. We can keep going. If we factor 12, let's see, we have 3 times 5, and then 12 is 3 times 4. So now we can cancel out 3. And so now we're left with 5 over 4 times 2. We can just combine 4 times 2 to 8. And we're left with 5 over 8. Now this is starting to get messy here, but this is just something that's going to happen to you every once in a while. But it's important to still organize your work. So all we're going to do is we're just going to write a divider here. It's no problem, no big deal. I'm going to go like that. And now all of a sudden your work is organized again. Is it perfectly symmetric? No, but who cares? Some people might care. I don't care. So that's the method that I like you to use. Again, you don't have to use it when in further courses, but I just want you to see what's going on there. This is actually it's a pretty powerful tool when you're dividing fractions. I was working with students a couple weeks ago where they couldn't reduce the fraction. They couldn't figure it out. And I couldn't figure it out either by using my multiplication facts, so I had to use this method. And these are middle school students. They're 8th graders we're talking about, and they couldn't figure it out. So they had to use this method, and So now see if you can use this method, and again, you're going to cancel out the common factors, and try 40, and when you're done, we'll come back and do it together. Again, I wouldn't use the factor trees. I would just use this method, but you can use the factor trees if you want. All right, we're back. So I'm going to keep the 4. And 80 is 4 times 20. So now we have common factors. So cancel out the 4s. And again, we're dividing both sides by 4. So 4 divided by 4 is 1. And that 4, so the 4s disappear and you have 1 over 20. So that one was pretty quick. Now, if you had trouble with that 1, again, that's okay. Just remember that when you cancel out, you're never going to end up with a 0. That's not going to happen when you're canceling. You're going to at the smallest number is going to be 1. All right. Actually, now that I think of it, I think the same thing is going to happen with 41. So try 41, and you're going to end up with 1 on the top. And when you come back, we'll do it together. So now we're back. I know that 72 is 8 times 9, but we don't have any common factors yet. So now we're going to do something that I haven't really talked about. You can always recombine the number. If you factor and you don't find any common factors, you might be able to recombine the numbers. So we don't have a 6 on the bottom, but if I factor 8 to 2 times 4 and 9 to 3 times 3, and then I recombine, I take a 3 and a 2, a 3 that I got from 9 and a 2 that I got from 8, and I combine them into 6. Now we have a common factor. So that's another tool that you can use. You can recombine, and now we can cancel out the 6s, and we end up with 1 over whatever 4 times 3 is, which is 12. And let's put our divider here. Actually, I'm just going to make this smaller. Right. So if you got 1 over 12, that's pretty good. These fractions are not easy to reduce. If you try to do it using multiplication, it's going to get pretty. Well, technically we are using multiplication, but if you try to do it by the old multiplication rules that we used in the 3 or 4 classes ago, you find it's going to get pretty tedious. So this is factoring is a powerful way to that is, factoring and canceling is a powerful way to reduce these fractions. Try 42, and when you come back, we'll do it together. All right, we're back. I'm going to keep the 6 there, and I'm going to factor 81 to 9 times 9. We still don't have any common factors, so I'm going to factor 6 into 2 times 3, and I'm going to factor one of the 9s to 3 times 3. And as you can see, we can cancel out. And, there's 2 3s in the bottom and 1 3 in the top, but we can't cancel out all of them. We can only cancel, if there's 1 in the top, then we can cancel 1 in the bottom. So be aware of that also. So then you end up with 2 over, if you cancel these out, you end up with 2 over 3 times 9, which simplifies to, and again, this is called recombining, or that's what I call it, recombining. 3 times 9 is 27. You don't want to leave it as 2 over 3 times 9. That's kind of it's just unnecessary to leave it to have 3 numbers when you can just write it with 2 numbers. All right, try number 43, and when you come back, we'll do it together. All right, we're back. So 9 times 5 is 45. And 5 times 20 is 100. Now you may not have known that 5 times 20 is 100. You can do it different ways. The 5's cancel out, and you're left with 9 over 20. You may have done it a different way. That's fine. If you got 9 over 20, then you did it correctly. You may have done 10 times 10 instead of 5 times 20. That's perfectly fine. All right. So remember I mentioned, so we know what factoring is, we know what composite numbers are, we know what prime numbers are, we know power notation, we know all that type of stuff, we know reducing fractions, we know the fundamental principle of fractions, we know we can multiply both sides of the fraction by the same number, we know we can divide both sides of the fraction by the same number, we know all that stuff now, right? And the most important thing to understand in this entire class is that we can use the fundamental principle of fractions to find equivalent fractions. Multiplying both sides of a fraction by the same number, dividing both sides of the fraction by the same number. We know we know all that stuff. But I mentioned greatest common factor. If we divide both sides of a fraction by the biggest common factor, then that's the fastest way to reduce the fraction. You don't have to do it the fastest way, but it just helps. It makes the problem go faster. So and so you don't need to know the greatest common factor, also called the GCF, or abbreviated GCF, but you're going to be expected to know what that is in other classes, so we're going to go ahead and learn it. So find the GCF of 40 and 32. All right, so the way that we do this is we take 40, and again, this is just the same thing that we've been doing. We're just factoring. You're learning factoring, you're learning all kinds of stuff. So 40 is, if you factor it completely to the prime factorization, you get 2 times 2 times 2 times 5. I'm not going to waste your time just by doing a factor tree or doing it by steps. I'm just going to go straight to the prime factorization. And for 32, we have 2 times 2 times 2 times 2 times 2. All right? So now let's say that you had a fraction, because the problem says find the greatest common factor of the following pairs of numbers. That's 40 and 32 are the pair, and use it to reduce the corresponding fraction. So the corresponding fraction we have down here is 32 over 40. So I'm going to show you how finding the GCF will help you reduce a fraction quicker. But I know this is sounding, really complicated. If you understand the fundamental principle of fractions and you know your multiplication facts, that's really all you need. This stuff just makes you a little bit more powerful when reducing fractions. So here's how you find the GCF. We factor the two numbers. The GCF is going to be the number, or the greatest common, the biggest number that you can create when you combine all the common factors. So we don't have any 5s down here. We have 1 5 up there. So 5 is not a common factor. We can't use 5. But we do have we have 3 2s up here, and we have 3 2s down here. Okay, we can't use these 2s because we don't have, that number of 2s. We only have 3 up here, right? So 2 times 2 times 2 is what's called the greatest common factor of 40 and 32. So what that means, so let's just go ahead and write that. 2 times 2 times 2 is 8, and that's our answer. That's the GCF. In fact, let's write GCF equals 8. Right? Now, again, you're probably thinking, well, who cares? Well, the reason that helps us in this class is because if you divide both sides of 32 over 40 by 8, you reduce the fraction as quickly as possible. You get to the fraction with lowest terms as quickly as possible. So you get 4 over 5. So that's why GCF helps us. It just helps us get to the answer quicker. So if you're thinking to yourself, this is too much information. It's too much to take in. Again, it's not super important right now that you know GCF. The most important thing is that you know the fundamental principle of fractions and so on and so forth. right? So see if you can find, using that method, see if you can find the GCF. Well, actually, let's do 45 together. You can do the next two problems on your own. So we're almost done. We've got a couple word problems to do and a couple more of these GCFs, and then we're done. So let's factor 90. 90 is 3 times 3 times 3 times 3 times 2 times 5. Now I didn't write that in order from least to greatest, but I don't really need to. I think you got the point with that. 110 is going to be 2 times 5 times 11. Yeah. So now the greatest common factor, there are no 3's down here, and there are no 11's up here, so we can't use 3's or 11's. So I'll just mark those. We can't use any of those. But we have 1, 2, and 1, 5 up here, and we have 1, 2, and 1, 5 down there. So what that means is that 2 times 5 is going to be our greatest common factor. Let me keep that highlighted actually. 2 times 5, which equals 10, is our greatest common factor. So now that we have the greatest common factor, we can reduce the fraction very quickly. 90 over 110, divide both sides by 10, and you get 9 over 11. So that's why GCF is useful. 10, 11, 9. All right, so now it's your turn. Factor 124 and 100, as you saw me do up here, and circle the common factors and then recombine them. I had to recombine 2 and 5 to get 10, which is the GCF. And I'd like you to write GCF equals 9/10 or 9/11, so I didn't do that. So that'll be the final answer. So try 46, and when you come back, we'll do it together. All right, here we go. Let's start with 100, the smallest one. That is, you may have done it in steps, 10 times 10, and then go on. But I'm not going to do it in steps because I just we don't want this class to go too long. So it ends up being 2 times 5 times 2 times 5. That's the prime factorization. 124. Sheesh. I'm not sure about that one. Let's see here. I'm going to have to do that in steps myself because I'm not sure what that would be. 60 would be 72. 8 times 9 would be 2 to the 4th power times 3 to the 2nd power. 2 to the 4th power times 3 to the 2nd power. 2 to the 4th power times 3 to the 2nd power. I'm just using powers in my head so I can remember what the heck I'm doing. Let's recombine those just to check. Recombine, you get... I actually did that one incorrectly. That should be 62 times 2, not 72 times 2. So 2 times 62... and then we can break 62 into 2 times 31. So it becomes 2 times 2 times 31. 120. Yeah, that's right. All right, so look for the common factors. We don't have any, we have 5's up here, but we don't have any 5's down here. So we can't use the 5's. So you can kind of just mark those out. I'll use red, meaning we can't use them. Red means no, or stop. And then there's a 31 down here, but there's no 31's up here. So mark that out. But there are 2 2's in the top and 2 2's in the bottom. So green means go. We can use these two. So 2 times 2 is the GCF, greatest common factor. And we can recombine to make 4. So what that means is we're going to take this fraction 100, 100 over 24, and we're going to divide both sides by 4. 100 divided by 4 is 25, and 124 divided by 4 is 31. So in the top we were left with 5 times 5, and the bottom we were left with 31. So you may be realizing as I'm doing this that this doesn't seem like the fastest way to do it. Well, you're right, it's not the fastest way to do it. The fastest way to do it is the way we were doing it up here when you were just writing the factorization and just canceling out. But why are we going through this tedious operation, the tedious way of doing this to find the GCF? Because you have to know what the GCF is. That's just something you're going to have to know in the academic world, in the math world. So try 47, and when you come back, we'll do it together. All right, we're back. So 66 is equal to, you can do factor tree, you can do a lot of different methods, but it's going to be, I think, 2 times 3 times 11, right? And 88 is going to be 2 times 2 times 2 times 11, right? So I'm doing a faster way to do it. I'm doing it a faster way. You may not have done it this method. That's fine as long as you got to this factorization. If you have that factorization, you did it correctly. If you didn't get that factorization for each problem, then that's fine. Just go back and figure out what you did wrong. So now we're looking for the common factors. We have a 3 up here, but we don't have any 3's in the bottom. So 3 is not going to work. But we do have an 11. We have 1 11 up here, and we have 1 11 down here, and we have 1 2 up here, and we have 3 2's in the bottom, but we can't use all of them. We can only use one of them that's common to the top. So 2 times 11 is the GCF, whatever 2 times 11 is. So GCF equals 2 times 11, which is 22. So now if we're going to use that to reduce the fraction as quickly as possible, we'll divide both sides by 22. Again, using the fundamental principle of fractions, we can divide or multiply both sides by the same number. 66 divided by 22, that's not one of your multiplication facts, but you'll see that it's 3. And 88 divided by 22, you'll see is 4. If you don't know those multiplication facts, if you don't know these multiplication facts, then that's okay. I didn't require you to know those. Remember, when you get above 11, it starts to become kind of a waste of time to memorize facts that are bigger than that. So now we only have 2 more problems to do. Obviously, we always have to do word problems. So there are some corresponding word problems you can do with these reduction of fraction problems. Number 48, 21 karat gold is 21 24ths gold. Have you ever heard of 18 karat gold, 16 karat gold? Actually, I don't know if there's 18 karat, maybe, I don't know. Have you ever heard of 24 karat gold, 16 karat gold? That carats, when you're talking about gold, carats is always out of 24 parts. So when you hear 21 karat gold, that means 21 out of 24 parts of the gold are actually gold. Gold is mixed with other metals to make it cheaper. All right. If you have 24 karat gold, then that means it's 24 parts out of 24, which means it's almost completely pure gold. So 24 karat gold is the best gold. If you don't have any gold, that's okay. I don't have any gold either. So we can identify with each other in that sense. Gold is a good investment, though. You want to buy it because it's not easy to reduce the value of gold as it is with paper money. But anyway, 21 karat gold means it's 21 out of 24. 10 karat gold is 10 out of 24 gold parts gold. 16 karat gold is 16 parts out of 24 parts. So that's what a carat means when you're talking about gold. So 21 karat gold is 21 24ths gold. What fraction of gold is 21 karat gold in lowest terms? So all this is asking is just to reduce this fraction. It's just an example of a word problem that you'll come across. So 21 over 24, we're going to divide both sides of the fraction. What goes in? Well, if you why don't you go ahead and try this? If you know your multiplication facts, then you know that it's going to be 3 is going to go into both of them. And you have 7 over 8. Now we could use a factor tree. We could use the method. In fact, I'm just going to show you the method where you factor. We could have written 3 times 7 and 3 times 8 and then canceled out the 3, but we didn't really need to do that. We could just skip forward because we know those multiplication facts. You only use that method when the numbers are too big and we don't have multiplication facts to go directly to the answer. But on this problem, we're going directly to the answer. Our multiplication facts give us the power to do that. All right, so now you try 49, and when you come back, we'll do it together. All right, number 49, 16 out of 18 people at the football stadium bought hot dogs. What fraction of people bought hot dogs in lowest terms? So we have the fraction of people, but we don't have the fraction in lowest terms. We know that if you know your multiplication facts, you know you can divide both sides by 2 and you get 8 over 9. Also, 2 just happens to be the GCF. So that's how that applies to the whole concept of GCF. All right, so that's it for today. That's a huge step in your academic life to learn fraction equivalency and all that type of stuff. So this is your homework. Get a screenshot of the homework. If you want screenshots of each page separately, there you go. That's page 1, page 2, and page 3, and page 4, and as usual, I want your homework to look exactly like this, except you're going to need space in between, the problems. So you're going to have a lot more pages than 4 pages. But as you can see, I'm keeping my promise. I'm not giving you any more than 30 problems. And I'm giving you the answers to the problems. But remember to put a name, date, course title, the title of the paper. Write the original problem down and show your work and rectangle your answers. And more important than anything else, check your work. If you don't check your answer, you're wasting 100% of your time. All right? Make sure you did it correctly. Do the homework completely and correctly. If it's not done completely and correctly, you didn't do it right. No matter what people tell you, you didn't do it correctly. All right, so that's the end of this class. And remember, if you don't do the homework, you can't go on to the next class because the information we're going to learn in this class is required for the next class, and so on and so forth. That's the way it is in this entire course. You must do the homework to continue. I'm your guide. I'm going to get you to the top of the mountain. The top of the mountain is finishing this course. I can tell you where to go, but if you don't actually follow me, that's like not doing the homework. This class is telling you where to go. You doing the homework is you actually following me and getting to the top of the mountain. If you don't do the homework, you're not moving anywhere. You're not moving 1 inch. All right? So you have to do all the homework completely. And when you're done with that, I'll see you in the next class, and I'll look forward to it.